I'm going to spend some time trying to understand a little bit of the basics of what we do every day and what we look at every day in cardiology. So we're going to focus on the electrogram, but many of the principles and that we'll be discussing apply to whether you're looking at intracardiac electrograms, ECGs, echoes, nuclear studies, MRIs, all of the things that we use on a daily basis in cardiology are basically processed signals. And believe it or not, it makes a little bit of a difference if you understand even just the basics of signal processing to understand that the signals that you're looking at are not true signals. They're all processed. And when you process signals, the concept is that you want to enhance the signal of interest. You want to enhance what you want to see. And that's why we go through all these processes. But in the process of doing that, sometimes you introduce artifacts. And if you don't understand what's going into the whole process, then it's a little hard to understand or to recognize when you have artifacts and when you have real signals. So a lot of what I'm about to present to you is really based on work that I did with an engineer, Jason Eng, when I was back at Northwestern. Jason has gone on to medical school, and he's now a fourth-year medical student, actually, at UIC. But really, I think has put this into a really nice, accessible format. For anyone who wants even more detailed understanding of this, Jason and I did put together a textbook shown here. It's Practical Signal and Image Processing, Clinical Cardiology. It really goes through, the first half of the book goes through all of the signal processing techniques that we use on a daily basis. Even if you don't recognize that they're being used, they are being used. And then how these actually impact all the various ECG and imaging modalities that we use in cardiology. All right, so if we're going to talk, and by the way, if we have, if people have questions, I think what's the best way to, I do want you to stop me, because there's no point in going on if you don't understand. Everything will build up, so we need to have a way for you to, let's see, can I turn on the chat here? For you to stop me, but I don't see how. Let's see how I can get the chat up. All right, so somebody's going to have to scream out and stop me if you have questions. So the first question is how to record electrical signals. There are a lot of different issues here: the instrumentation, the basic signal processing. We'll talk about what it means to do things in the frequency versus the time domain. And again, whether you realize this or not, a lot of the imaging techniques that you're looking at are looking at things in the frequency domain. We'll talk about the types of signals and then integration. All right, so this is a basic electrocardiogram, and there are a couple of important things that you need to know about the electrocardiogram that just have to do with signal processing. So first of all, when I started as a medical student, we were doing analog ECGs. Currently, what we have are digital ECGs, and digital ECGs provide a lot of important benefits in that, number one, they're easy to store and easy to retrieve via computer, whereas analog ECGs are much more difficult to do that. But in order for us to understand what a digital ECG is, you have to understand that the signal that you're looking at here is not continuous. It seems like it's continuous, but it's not continuous. By definition, a digital ECG is an ECG that's sampled at a certain rate. Most systems, and we'll talk about why, will sample at around 250 hertz or 250 cycles per second, 250 samples per second. So that means every 4 milliseconds you're getting a sample point. So you're missing the data that's sort of in between 0 and 4 milliseconds, if that's important to you. A couple important things to look at down here. So you see here, this thing is says 100 hertz here. So what does this mean? So the other thing that we do in ECG signal processing is we do what's called bandpass filtering. So what bandpass filtering does is it basically just includes certain frequencies within the ECG and then excludes the other ones. So just so nomenclature, so bandpass filter, for example, could be from 0.05 to 100 hertz. And that means that you're including the frequencies that are in that range. A low pass filter will basically do that. It will allow the frequencies below some value to be included and then excludes the higher frequency. And a high pass filter basically allows the high frequencies to pass through and excludes the lower frequency. So a bandpass filter is basically a combination of a low pass and a high pass filter. So the low pass filter here is set at 100 hertz, and the high pass filter is typically around 0.05 hertz. The other things that you'll see here, of course, listed is the calibration in terms of the amplitude per millimeter, and then the paper speed. And then this cal signal is very important to look at. It should be a rectangular wave here, just like this. And this tells you that the machine is calibrated properly, right? This tells you that the size should be 10 millimeters, which corresponds to 1 millivolt. So it's a 1 millivolt cal signal. And this duration is supposed to be 25 millimeters. Okay? I mean, it's supposed to be 1 box, basically. So this is, and it's important to understand the ramifications of this signal processing because, for example, when you find it difficult to see pacemaker spikes, pacemaker artifacts on an ECG, just consider the fact that a pacemaker stimulus is typically half a millisecond, 0.4 milliseconds in that range. And remember, I told you that the ECG is typically sampled every 4 milliseconds. So how likely is it that you're going to pick up an ECG signal of the pacing artifact that lasts only half a millisecond if you're sampling every 4 milliseconds? It's very unlikely. So there are processing techniques that we have to introduce to sort of make up for that. All right, so the basic block diagram for an electrophysiologic recorder, and again, this is whether it's ECG or intracardiac. You have some electrodes. You have to amplify the signal. In the old days, like when we had our analog ECG machines, it went through analog filters, and you could still implement analog filters and then do analog to digital conversion. So this is where you have a continuous signal, and then you sample it, and then you have your digital components. You can then proceed, if you need to another microprocessor where you can do further digital filtering and other digital processing, analysis, and diagnosis, and then you have the display storage issues that you have to deal with. Now, this is, again, this is true not only for electrical recordings, but this is a process that's very similar to what we do with echocardiography, what we do with MRI, CT scans, etc. So this is not unique to electrophysiologic recording, but you can see you're taking your raw signal over here, and by the time it gets over here to when you see it, because this is where you see it, this is the display, the signal has been changed a lot. It's been amplified, it's been filtered, it's been, undergone analog to digital conversion. It's had more filtering and signal processing. So again, you're looking at a processed signal, not at the raw signal. Even though it seems like you're looking at a raw signal, it's really the processed signal. Okay, so we talked about that. All right, so let's just define a few things here. So this is just to show you unipolar and bipolar recordings. So our recordings of electrical signals are basically voltage-based, right? We're measuring voltage on the surface ECG. We're measuring voltage, right? So to measure voltage, you have to basically do that across two poles, right? There's no such thing as voltage at one spot. So voltage is always a potential difference between two areas. So we talk about unipolar signals, but unipolar signals are truly not unipolar because you have to measure your voltage relative to some other point. So basically, unipolar signals are measuring your voltage at a particular site compared to essentially ground or some distant point. So the distant point basically has no impact on the local voltage. And so it gives you sort of a broad field of view compared to bipolar. So for example, if you look at a signal here, there's a unipolar at point A, unipolar at point B is 5 millimeters apart. And then the bipolar signals are basically just the difference between the unipolar and the bipolar, between the two unipolars, sorry. So you can see if you just take the difference signal here, all of a sudden you get a much sharper signal. And what you'll also see, for example, this happens to be a recording in the atrium. So you can see this is the atrial potential, this is the ventricular potential. Now, because the catheter is sitting in the atrium, the ventricle is sort of far away. And the ventricle looks more or less the same to the recording site at point A as it does at point B. So when you do bipolar, it basically eliminates these far field signals. Okay? Skip that. All right. So now we'll move on to a couple other topics. So frequency analysis is also very, very important. And again, a lot of the signals that we're looking at, and in particular, we're looking at a lot of frequency analysis for atrial fibrillation. So it's a little bit important to understand what we're talking about when we're talking about frequency analysis. And for those of you who are not inclined to think about this in in tremendous depth, just think about all the frequency analyses that you have in real life. So, for example, you tune a radio to a particular station, right? That's frequency analysis, right? That's you're combining a sound signal with the carrier frequency for whatever that radio station is. So you're looking at that. If you adjust the treble and bass on any kind of recorder, you're again doing frequency analysis and processing because you're adjusting different frequencies in terms of the sound that you're hearing. So these are things that are really commonplace in our lives, even if you don't understand a lot of the underlying issues. So the frequency domain was really a lot of the original mathematics behind this was done by Jean-Baptiste Joseph Fourier way back when. And basically, you don't have to know, nobody needs to know this formula, but all you really have to understand is that what he really figured out here is that you can decompose any kind of signal, or most of the signals that we're interested in, into a sum of sine waves. So let's try to understand how that might work. So here you have a sort of square wave, right? So this is a signal, right, that we might see in some kind of application. And what we want to do is we want to say, all right, let's decompose it into sine waves. So the frequency of that signal was 0.5 hertz. So as a first approximation, we would start with a sine wave that has that frequency. And you can see it really doesn't look very much at all like the square wave. But what we can do then is we can add more sine waves. So now we're going to add a sine wave at a frequency of 1.5 hertz. And look what happens. All of a sudden, the signal now looks a little bit more like a square wave. Now we're going to add another sine wave, 2.5 hertz. And look again, the signal now looks even more like that original square wave. And here we add another sine wave, and you can see the signal becomes much more like this square wave. And if you add enough of these sine waves, you can actually reproduce the square wave. So that's the basic concept of frequency analysis. Is it instead of building up a signal into it and making the original signal, it actually just breaks down the signal into its component frequencies. And then once you break it down into the component frequencies, you can try to understand, what frequencies contribute to the signal and which frequencies you might be interested in, because you may not be interested in all the frequencies. So this is just a plot showing if you take this original time domain signal of a square wave and break it down into its frequency components. These are all of the, you need to know also which frequency and how much of it to add. So obviously for the 0.5 frequency, you need a lot of it. For these other frequencies, you need much smaller amplitudes. And then, so this plot is basically a frequency domain plot of this signal. Fourier, won't talk about this, but too much. There are two types of Fourier analyses. Most of what we're going to do is in the discrete area because we're using digital signals. And so we use this technique called the fast Fourier transform. The important thing to know, and this is very, very important for a lot of applications, so the frequency resolution of the signal is going to be 1 over the length of the signal. So if you have a signal that lasts for 1 second, the frequency resolution is going to be 1 over 1 second or 1 hertz. The frequency range that you can look at is from 0 to half the sampling rate. Now, who can tell me one application that this is very, very important in something we look at every day? Anybody?
The Nyquist limit in echo.
So that's exactly what the Nyquist limit in echo is. That's 100% correct. And it just comes from basic signal processing, that if you can't detect frequencies above half the sampling rate. And let's see if I can show you why. Now, I think I have a slide here. Let's skip this. So important things about filtering, and again, all the signals that we see are filtered, whether you know about it or you don't know about it. But when you looking at signals, you want to make sure you keep it within the dynamic range of the amplifiers. So what that means is you don't want to saturate your amplifiers because otherwise you lose your signal. On a constant basis, we're always trying to improve signal to noise ratio because that allows us to see the features of the signal unobstructed by noise. And then sometimes we use processing techniques to enhance specific features of the signal. All right, so one of the things that we use a high-pass filter for, okay, and this is very, very important, for example, in the electrocardiogram. If we would not use a high-pass filter in the electrocardiogram, you would see a lot more wander than we see in many of our ECGs. So those recordings would wander all over the place. So what the high-pass filter does is it allows you to reject that baseline wander due to motion artifact, and it'll also bring your baseline to zero after loss of electric contact or defibrillation shock. So you see that happen all the time when you do a cardioversion, for example. Your cardioversion introduces several hundred volts into the body, but you get your signal pretty much right back after doing that. And remember, the signal that you're looking at is on the order of millivolts. So think about what it must take to when you put a several hundred volt signal into the body and you want to record signals that are in the millivolt range. So this is what helps you to be able to do that. So we talked about these very low frequencies allow you to remove motion artifacts. We filter out very high frequencies. So for example, muscle and nerve activity will have very high frequencies, and we can remove those by using a low pass filter. What's very interesting is Peng Cheng Chen from Indianapolis, now back in Los Angeles, has developed a technique using ECG electrodes, and what he does is instead of looking at the typical range of frequencies we look at for ECG, he's looking at now these high frequencies, and he's shown that he can actually make recordings of sympathetic nerve activity by looking at these very high frequencies. So again, just looking at the same signal, same electrodes, he's able to tease out the nervous system activity. One of the things that we are constantly frustrated by is our power comes in at 60 hertz. That's the normal voltage that you get out of your socket that you plug your equipment into. And that creates a lot of potential interference in our signals. So a lot of the equipment that we have has to adjust for that. And you can see an example of this here. This is again a recording that's made in the atrium. So you can see an atrial signal, a ventricular signal, and then in between you see this oscillation. It looks like a sine wave, and in fact it is a sine wave. It's a sine wave that's occurring at 60 hertz from being connected to the wall socket. And if you looked at that in the frequency domain, you see a lot of frequencies here that represent the signal, and then you see this sharp peak here at 60 hertz, and that represents this piece of the signal. So what you can in theory do then is, if you recognize this, you can sort of identify this particular band and create a band pass filter that basically excludes this piece of the signal. And when you do that, it's called a notch filter. So you can see now that 60 hertz spike has been essentially removed, and you can see that you don't really have much more uh, 60 hertz noise. So it's a very effective way to remove noise from your signal. And you can see it did not destroy at all the quality of the signal. So here's just another example of what a high-pass filter might do. So here you see a recording. This is an unfiltered bipolar recording. You can see, I think it's also from the atrium. You can see the atrial potential, and then you see this, elevation, this repolarization artifact. Now, if you're not interested in the repolarization artifact and you're really only interested in the depolarization signal, you can see this is a very high frequency signal. It's a sharp signal, so it has a lot of high frequencies. Or this is not such a sharp signal, so this has fairly low frequencies. So if you want to get rid of the low frequency signals, what you can do is use a high pass filter. And when you do that, all of a sudden those repolarization signals go away. And now you can focus only on the sharp depolarization signals. So this is the power spectrum of that signal. This represents mostly the repolarization signal, and then this represents the depolarization. We filtered this out, and now we have none of that repolarization signal. So here's an example of how we can actually also use frequency analysis to our advantage. So this is a recording made in the atrium of atrial fibrillation. You can see the rapid rates, and you can see the changing morphology of the signal. So you can see if you wanted to know how fast the signal was going, you could say, you could mark each electrogram and calculate the intervals. So that would be something like this. Say, here's where all your atrial signals are occurring. And then you could say, all right, now figure out how fast that is. And in this case, you see it's 220 milliseconds. And that's approximately 4.5 hertz. So remember, 1 hertz is basically 1 cycle per second. So that would be 1,000 milliseconds. Right, between, in terms of frequency. So that's basically how you get the calculations back and forth. So the only thing to note here is that manual or automatic marking can be very difficult. So here you see a very clear signal, but here you see a very low amplitude signal, and how do you decide which kinds of signals do you mark or do you not mark? So here, for example, is another low amplitude signal. Is this another recording? Do you count this? Do you not count this? So you can see here, if you set a threshold such that these weren't counted, and you see here another one that's not counted, then you're going to miss some of the recordings. And in this case, then you calculate out a frequency that's not as fast because there aren't as many signals. Now, which one's correct? It's hard to know, right? Should this count as a signal or not? So one way to overcome that is to do this in the frequency domain. And what you do is you basically, like I said, take this signal, you break it down into its frequency components. And when you do that, you can see that there's this dominant frequency here at 4.2 hertz. So this better represents the activation rate of this signal. And it's much easier to do than it is in the time domain. And that's why we do things in the frequency domain, is that it's easier, sometimes it's easier to work in the frequency domain than it is in the time domain. Any questions so far? Everybody's quiet. Okay. So again, I just want to make sure everybody understands this is processing. So every time we touch a signal and we change the signal, there are pitfalls. And there's, some of them are listed here. double potentials, low signal to noise ratio, far field ventricular components in the signal. All these things can basically affect your dominant frequency analysis. And you can't just assume that you're taking a signal, you put it in a black box, you get an output, and the output's correct. There are many things that can screw up the analysis here. So you have to understand both the raw signal, the processing, and the output to really be able to interpret this. All right. So here's the reasons that we, a summary of why we do, why we filter. So again, this is very important. We have to sample the signal without aliasing. Again, goes back to the Nyquist limit that hopefully everybody's familiar with in echo. Want to make sure to keep the signal within the dynamic range of the amplifier so we don't saturate and lose information. And then improve the signal to noise ratio. Like we talked about, there's motion artifacts, muscle noise, power line interference, and then enhance specific features. So that's really why we do all this processing. So just a little bit about analog versus digital filtering. So you can filter signals both analog or digital, as I mentioned before, and sometimes there's good reason to do both. But analog basically is using the hardware to actually filter the signals. And that's, as you see here, a combination of resistors, capacitors, and amplifiers. This is a circuit for an analog filter. But this is something that's built into the machine. It's not written into the software that's processing the signal. It's got some advantages in terms of it minimizes delay and distortion. But it does have complex specifications. It's not easy to change. In fact, you can change it once you have the hardware, and it does require more space and power than digital processing. So this is the way digital filters work. It's just basically taking the signal and doing mathematical manipulations, by programming the software. So here's a sample of what this is basically a step function. So you can see here the points start at 0, and then you have a step up to 1. Okay, now one of the very common things that we look at is a moving average. And going to modern times of our COVID environment, everybody's talking about moving averages, right? So we talk about our 7-day moving average, our 14-day moving average. That's a signal processing technique to try to smooth out some of the abrupt changes and the day-to-day changes that we see in the COVID numbers, and try to get a better understanding of what's happening over time. So you can see, again, this is something that we use in our daily lives. So the way a moving average works, it basically takes, if you start over here, it takes the last 3 signals and averages them and replaces the value with the average value. So the way this one is designed, it actually takes the data point, the preceding one, and the next one. So that's the way this digital filter is designed. So you can see here, when we get over here, it averages 0, 0, and 1, you get 0.33. You get over here, it averages 0, 1, and 1, and you get 0.66. And then when you get up here, it averages the 3. So you can see what it does is it takes the step function and now is spread it out. So the reason that we use the digital filters, as we said, it saves space and power. It's easier to modify. It's just software, so you can constantly change it. But it does create time because the computer or whatever it is that you're using has to spend some time to process it and to run all the mathematical steps to basically enable the filter specifications, and it is subject to more distortion. All right, so here's an example of why the Nyquist limit is really, really important. So we're going to take this 8 hertz sine wave, and we're going to sample this at 10 hertz. So we're going to sample the sine wave faster than the sine wave is changing. Okay, so now we've sampled this at 10 hertz. Okay, and what we're going to do is we're going to reconstruct the signal based on our sampling. And if you take those points, we've now reconstructed the signal based on these points that were sampled from this 8 hertz sine wave. And you can see what we get is not an 8 hertz sine wave, we get a 2 hertz sine wave. Okay, and this is because we didn't sample fast enough. In order for us to reliably reproduce our 8 hertz sine wave, we have to sample at 16 hertz or more. Okay, so at twice the frequency that we're interested in, because otherwise we end up losing information. Okay, does everybody understand this Nyquist limit and this point of sampling?
Dr. Goldberger?
Yes.
So when this alliance, I mean, I know that we require at least to sample the signal twice, right? I mean, I don't get sometimes that concept. What happens when you sample twice and that frequency is too high? So you can produce alliance, but we can make, how you make sure that you are sampling enough?
So it depends on the frequency that you're interested in, right? So if you're not interested in frequencies of 10 hertz, you have to sample of 8 hertz, I guess. If you're not interested in frequencies that are that high, you don't have to worry about it. If you're only interested in frequencies that are 5 hertz or below, this sampling rate is fine. You're just not going to be able to detect more rapid fluctuations. It doesn't mean that they're not there. It just means that you're not going to be able to detect them. Does that help?
Yeah, thanks.
Right, so this is where understanding what it is that you're doing and how it alters the signal. If you undersample the signal, it doesn't mean that the frequency components in the original signal aren't there. They are there. You just haven't sampled fast enough to be able to detect them.
Dr. Goldberger, I have a question. If you sample faster than the signal itself, like you sample more frequent, are you going to get information that's not there, or it's not gonna matter?
No, you will no. I mean, you can't add information to the signal. You can only deteriorate information from the signal by sampling.
Okay, so it makes sense just to sample to get the sample more frequent, even if you are interested in low frequency. It's not gonna change.
Right. So remember, there are trade-offs. So the more you sample a signal, the more storage you need to store it. Right. So
okay. So the downsides of it.
Right. If 100 hertz sampling is good enough, and you're sampling at 1,000 hertz, you require 10 times the storage.
Okay, got you.
So you really need to think about what it is that you want and how best to do this. So just imagine, So for example, in the EP lab, we do sample our intracardiacs at about 1,000 hertz, so 1,000 samples per second. ECGs are sampled, I think, at around 250 hertz, so 250 times per second. But just imagine if you quadrupled the storage needs for a whole health system based on increasing your ECG sampling from 250 to 1,000 hertz. Think of the cost and that will incur.
Got you.
Okay.
Thank you.
So it's a great question, but it's not a trivial issue. Okay, so this is basically what we talked about in terms of the Nyquist limit, and I think this is, if everybody walks out of here understanding the Nyquist rule, you know, then I think we've accomplished a lot, because you can see it's around in everything, in echo and ECG. So again, ECGs are sampled about 250 samples per second. So we are not going to be able to detect frequencies above 125 hertz. So as I mentioned, this recorder that that Pengsheng Chen is doing to use ECG electrodes to record sympathetic skin sympathetic nerve activity. Because nerve activity is much higher frequency than this, we can't use standard ECG signal processing. We have to use different kinds of processing and sample at a much faster rate to be able to detect those kinds of frequencies. All right, so this is an example of what I was trying to tell you earlier about you know, the sampling of pacemaker impulses. So here, for example, is an original signal that has pulses of 0.1 milliseconds duration. So these are shorter than typical pacemaker pulse. But we're now going to sample the signal at 1,000 hertz. So that's one sample per millisecond. That's 1,000 samples per second. So one sample per millisecond. And you can see, even if you sample this signal, which lasts 0.1 milliseconds, right? You're taking one sample per milliseconds. You sample it, you're going to miss a lot of these artifacts. And that's what happens a lot in an unprocessed ECG. If you were not to process the ECG, you would almost never see the pacemaker effects, because you're not sampling at a fast enough. So this is where some of the analog filters that are incorporated into ECG machines actually are helpful, because now what we do, instead of using this raw signal before we do our digital sampling, what we'll do is we can actually use a low pass filter, in this case at 400 hertz. And when you do that, what you've now done is you've degenerated this this pulse into this kind of waveform. And you can see that this signal is now much wider, right? Is much wider than the original signal was over here, right? This is very sharp, really occurring only at that one point, and now it's a little bit more broad-based. And because it's more broad-based, you're much more likely to pick up that, you know, part of this with your sampling at 1,000 hertz. So you can see how we've now taken our raw signal, done some analog processing to basically enhance it in our detection, in our analog to digital conversion. And you can see there's some variation in amplitude, and that's because you're not always detecting it at its peak. Sometimes you may be detecting it over here. But this is a technique that allows us to, you know, for example, pick up pacing artifacts, both on ECG and on the monitor. Telemetry monitors also are very, have even lower sampling rates than a standard ECG. Okay, so this is also very, very important for us to know. So we talked about this already. Somehow this got duplicated here. All right. So a lot of these things are what we call anti-aliasing filters, and that's really to remove that process of filtering. or the adverse effects of filtering and adverse effects of undersampling, really. And this is, again, a note of caution that you have to be careful when you use filters. Filters will also attenuate frequencies of the signals of interest and affect measurements. So, for example, if your signal has a lot of 60 hertz components and you use a notch filter to eliminate the 60 hertz power noise, you're also going to eliminate the 60 hertz components of your signal. So it doesn't come without a cost. All right, and let me just find one last thing here that I wanted to show you, and then we'll open up the questions. Oh, I didn't have it. All right, I'll have to, this is obviously there's a little more here to go through, which we can do at another time, and I thought that slide was in here, but apparently not. All right, so any questions about this? Does everybody understand some of the basics, some of the basic issues here? All right, a lot of silence. So I would encourage you to, whatever rotation you're on, whether it's EP, whether it's Echo, whether it's the cath lab. I mean, there's a lot of digital processing that goes on in the cath lab, MRI, nuclear lab. Try to, figure out what is the raw signal and what is the process signal, and how you got from beginning to end. And I think people do talk about some of the artifacts that you might see from signal processing, but if you understand a little bit about what's going on, it'll make, I think, a lot more sense for how these artifacts got introduced. All right, if there are no questions, I'm off to clinic.